Now let's talk about computing global minimum variance portfolio. And in this example, or in this setup, suppose that we have actually three assets for simplicity. So actually, we are trying to minimize this portfolio variance, which is given here. And our constraint is that the sum of investment weights in each one of these three assets, the sum should be equal to 1. So actually this same thing can be written explicitly like this. Okay. But you can have more than three assets, of course. So the same thing applies if you have n number of assets. There is no difference. And the Lagrangian function can be written in this way. So you can see we have the objective function and we have the equality constraint multiplied by our Lagrangian coefficient lambda. And then what you need to do is write down the first order conditions. And here you need to take the partial derivative of this Lagrangian with respect to each investment weight mi. But simply we can represent this in vector notation. And what we get, since this is a quadratic term, you are taking the derivative of these quadratic terms with respect to each mi. And this can be simply written as a vector. So notice that here this sigma is the covariance matrix. So this sigma is actually 3 by 3 and this m is actually 3 by 1. So what you have here is actually a 3 by 1 vector. Okay, so you can verify whether the dimensions match. And then you can notice that this vector of 1s, this is actually 1, 1, 1. Again, a 3 by 1 vector. So what you get here is also a 3 by 1 vector. And then the next partial derivative we need is with respect to lambda. And since we have only one constraint, this is just a single partial derivative. And if you apply this partial derivative, what you get is our original constraint. Okay. So the question is, how can we write now this as a system of linear equations and apply what we have seen before in this chapter? And you can see that this can be written as now 2 sigma, and then you have this vector of 1, right? So basically I am writing my m, okay? So 2 sigma is multiplied by this m, and then I have this 1, and then my next term is going to be this lambda. And notice that here this is a vector of 1s actually. And then I have this vector of 1s, and then I have no lambda term in the second equation, so I can write 0. So you can see that 1 times m, and then the right hand side we can write down. The right hand side is going to be, for the first equation you have 2 sigma times m plus 1 times this lambda equals to 0. And notice that this is actually also a vector of zeros. Okay, and this is actually a vector of zeros 3 by 1. And then the next term we have this m times 1. This is going to be a transpose here. And then we have 0 times lambda. So this should be equal to 1. And this 1 here is a scalar. Okay, so this is what we have here. You can see we have 2 times sigma and 1, 1 transpose and 0. So we can write this as a system of linear equations now. So just as we have done before, so remember that when we solve system of linear equations, what we considered was like a times x equals to y, right? This was the setup before. So you can define this matrix as your A, and this is the vector of unknowns, let's say x, and then you have the right hand side y. So in order to solve this, as we have seen, if you want to apply, let's say, Gaussian elimination, it is obviously you can get this x as a backslash y. So this is using the Gaussian elimination technique. And notice that when you solve this system of equations, what you are going to get, the first three elements of this solution, right? You can also use the inverse, obviously. So going back here, this x is also given by a inverse times y, right? So if we write the solution as z, not x, then this can be written as A inverse B, and the first three elements of Zm are the portfolio weights that we are looking for to obtain the global minimum variance portfolio. And once these minimum variance portfolio is obtained, you can get the portfolio's expected return for this particular optimal M, and you can also calculate what is the global minimum variance portfolio's variance.